Hello everybody, I am Matthew Godat and this is my lab number 2. Starting with our introduction, the purpose of this lab is to use gathered data from Tracker and measure and create closed script code that models the effects of drag. And the principles we're going to be using are Newton's second law, which is force is equal to change in momentum over change in time, and the drag force equation. And we will discover that the force of drag acts opposite to the direction of motion and slows an object. For the experiment, a paper ball was filmed being thrown into the air with velocity in the x and y directions, and the trajectory was then traced in a tracker software, giving position over time data. Our system is the paper ball, and the surroundings are Earth and the air. And our initial conditions is velocity in the positive x and y directions, and we begin at an elevated start position. Here's a screenshot of the tracker software used to trace the data. You can see the parabolic tracing of the ball in these sequence of tracker points. The distance was calibrated using a meter stick in frame, and the axes were placed relative to where the ball was initially released, and then where the ball will eventually land. Moving on to the code, we take the tracker data and update the given starter code with our initial conditions. You can see that we update our ball's mass, the initial position, initial velocity, and eventually our drag coefficient. And using Newton's second law, we can also begin to calculate the net force. So first we need the force of gravity, which is force of gravity is equal to mass of the ball times g, and we start calculating that here in the code. And then to find the net force, we need to add the force of drag. So the force of drag is calculated here and then added here. And then using this new net force, the position and velocity are then updated in the while loop. And then we set our time to t equals 1 because that fits our code best. You can see that here. And then we modify our coefficient b to better simulate the drag. Here's a screenshot of the code output. You can see these arrows point in the direction of all of our forces, and then we get all of these different graphs that document our findings. So to analyze our data, we plot all of these trajectories of both of our computer studies and our tracker study against each other. And you can see that the tracker experiment does not follow a perfect parabolic trajectory. And this is likely just due to error placing the points in the tracker. The camera frames become blurry when filming such a small object. The CPU drag model also intersects the x-axis way before the tracker model, which means the coefficient b is too high. So what questions can we answer with this data? What does it mean? The computational model simulating drag does predict an eventual terminal velocity. When the air resistance is equal to the force, we experience this terminal velocity. And if we extend the time limit on the while loop to simulate the object free falling for a longer period, we would see this terminal velocity reached. You can see this in this graph here, where eventually the rate of change of velocity becomes constant, or becomes 0. So the second question, what if the object were thrown straight up with the same initial speed, and this would have no effect on the time it takes the ball to reach the ground? All of our forces in the y direction are still the same as the previous model, so it would take the same amount of time. Thank you for listening, and I hope you greatly enjoyed this Lab 2 physics presentation.